All right, so this chapter is on forces and motion. Okay, so we'll study some of the different forces that we encounter in life, and forces you'll see that cause acceleration. Okay, okay, so here's an example of a force that you're exerting. Okay, so you're exerting a force on the syringe. Okay, and that force gets transferred to the tip of the needle. Okay. So a force is a push or a pull. In this case, it's a push. Okay, it's an interaction between an agent. This is the agent of the force, and the object. So the object is the syringe in this case. Okay. Uh, we'll study something called a free body diagram, or we'll use free body diagrams. These are just simplified representation of the situation. Okay. Now here's something that's going on here that is not mentioned. Okay, so I'll demonstrate to you here. So let's say I push with my thumb with a force of 10 pounds here. Is that hurting? No. Okay. I'm going to push with the same 10-pound force now. Is that hurting? I'm sorry?
Maybe.
Yeah, it is. All right, so what was the difference? It was the same force, 10 pounds.
The object. It was the point of contact that was the difference.
So what is relevant is, okay, so, and we'll talk about this later again, the pressure, which is force divided by area. For the same force, if you're applying it over a much smaller area, the pressure can be much larger, and that can break your skin. Okay, and also greater pressure leads to more greater pain. Okay. All right. We'll talk about equilibrium. Equilibrium is, so there are two kinds of equilibriums. One is a static equilibrium, meaning the object is at rest, and a dynamic equilibrium when the object is moving, but it's moving at constant velocity. All right, we'll be interested in mostly static equilibrium. Okay, so the object is rest. When an object is at rest, the sum of all the forces acting on it are zero. Okay, or the total force acting on the object is zero. So here's this girl, this gymnast. She's in equilibrium. She's at rest. Okay. Now we'll learn over the course that for her to be at rest, what needs to be true? Do you guys know what should be true? Okay, so for instance, when you're standing, you're in equilibrium. When you're in equilibrium, what is true? Can you fall down, for instance? Okay, so I lean back, I fall down. I lean forward, I fall down. What happens?
Leaning is a force.
Okay.
So there would be zero force for the.
Okay. So here's several ways to look at it. So when you're in equilibrium, so here's your footprint.
Balance.
Okay, your center of gravity needs to be above your footprint. Okay, so for instance, when you're standing, what is your footprint? The space between your feet is your footprint. Okay, so if you don't want to fall down, then your center of gravity needs to be above your footprint. You want to fall down, all you have to do is bring your center of gravity outside your footprint. Okay. So, for instance, if she brings her foot in, she'll fall down this way, and so she'll have to lift her foot back in to bring her center of gravity back into the footprint. Okay? Objects at rest are in mechanical equilibrium. Forces are necessary to keep an object in equilibrium, but the net force is zero. Okay? So if an object is in equilibrium, if there are several forces acting on it, the sum of those forces are zero. Yeah? So the gymnast is in equilibrium because all the forces acting on her are exactly balanced, meaning they've added up to zero. Okay? What if the forces don't add up to zero? Then you accelerate. Okay, so if you want to accelerate this object, you have to apply a net force on it. Okay? The forces can't be zero. Okay. And Mr. Newton realized this. Okay, so what Mr. Newton realized was, see, he gave us this equation. This is Newton's second law. What he realized was the greater the force, the greater the acceleration of the object. Okay? And for a given force, the larger the mass, the smaller the acceleration. Okay? So you can apply a force to a semi-truck and it won't accelerate as much, and you apply the same force to a small car, it'll accelerate greater. Okay? So a larger acceleration requires a larger force. A larger acceleration requires a larger force. So this is Newton's second law. Okay. So organisms use forces to support themselves and to move through their environment. Okay. So, my weight is being supported by my legs and stuff like that. So if I became an elephant, like we saw in the last chapter, what would I need? My legs would need to be stronger. They're supporting a greater weight. Okay. So that's my body structure is determined by what kind of weight I have to support. So in this chapter, we'll study how forces give rise to movement and how forces balance for an object to remain, must balance for an object to remain still. Okay, so what this is saying is the following. Let's say something is moving. Do you need to keep applying a force to keep it moving? Okay. So for instance, here's this object. I'll get it moving. It stopped. Why did it stop?
There is no more force.
I'm sorry?
There is no more force.
Well, as soon as I
The force of the friction
Stop.
was more than the force in your push. So
So,
it's not-
well, once it left my hand, I was not pushing it anymore. So the friction force stopped it. Okay. Now, if I reduce the friction, what will happen? If
We'll
it
go further.
will go further. What if I remove the friction?
And there's no stopping force.
So it would never stop. Okay. But see, that was not easy to realize first, because in everything that you do, there's always friction. Mr. Galileo, back in the 1600s, he reduced the friction. He gradually reduced friction on objects, and he realized that if you could remove all the friction, then the object would keep moving forever at constant velocity. Okay. In fact, you guys have experienced this. Here's one place where you can experience it. In an air hockey game, you see that puck in an air hockey game. That puck without any friction, if the table was long, let's say from here to Orlando, you hit it once and it could go to Orlando. Okay, so forces are not required to sustain motion in an ideal frictionless world. Of course, we encounter friction all the time. Okay? But organisms always live in environments with dissipative forces. Okay? Friction forces are called dissipative forces. Why are they called dissipative forces? Okay, so let's see why they're called dissipative forces. Let me put this again. So when it was moving, it had something called kinetic energy, the energy of motion. Okay. Can you destroy energy? You cannot destroy it. So what happened to that?
It dissipated it on your own.
Okay, so do you guys know the law of conservation of energy? Okay. So again, it just states energy cannot be created or destroyed. Okay. So since you lost all the kinetic energy, something must have happened. it got converted to heat. Okay. So the friction force converted the mechanical energy to heat. Okay, and heat is the worst form of energy, so that's why friction forces are called dissipative forces. They convert good energy into bad energy. Okay, so friction and air resistance are dissipative forces. Yeah. So yeah. Forces needed for support and locomotion are important reasons why organisms that live in water have very different body structure than those that live on land. Okay, so let's understand this. All right, so when I'm standing, my weight is 165 pounds, something like that. And what is that? That's the force with which Earth is pulling me. Okay? Why am I not going into the ground?
Because the same amount of force exerted
The,
back on
yeah,
you.
the ground is exerting 165 pounds on me. Okay? Now my body structure has to be strong enough to bear that. Okay? Now let's look at this. So let's say if I lived underwater. Yeah. Underwater, Earth would still be pulling me with a force of 165 pounds. Yeah, it's still pulling me with a force of 165 pounds. But if you're underwater, the water pushes you up. Okay, that's called the buoyant force. Okay, and the buoyant force is almost equal to your weight. So underwater, actually, you would feel weightless because the water is pushing you up, the Earth is pulling you down with that force. Okay, now the ground doesn't have to push you up. The force with which the ground is pushing you up is almost zero. You feel weightless. In fact, astronauts, when they want to train for space travel, they train underwater because that's one place where you can feel weightless on Earth. So if I live all my life underwater, do I need to have bones this strong? So your body structure is dictated by your environment. Okay? So the forces that you have to bear and so on. Okay? So organisms that live underwater, organisms that live underwater have different body structures than those that live in land. Okay? So now here's another thing. Here's a structure that is dictated by what you want to do. So a dandelion seed floats in the wind because the drag force. Okay, so here's a dandelion seed. Okay, and why does it have these structures? Hairy structures. Okay. So what happens if I drop this object? This falls straight down. Is there air resistance when this falls down? It's very negligible, and so it falls down straight. Okay. So the drag forces are almost negligible. For this guy, in the dandelion's seeds, what it developed these structures evolved so that when it's trying to fall down, the air will catch it, like we said, and the drag force is almost equal to the weight, and sometimes greater. And so the seeds can be transported long distance and spread. Okay. So you see these structures evolved to increase drag forces and to disperse the seeds. Okay, so Newton's first law says, so again, we ask the question, do you need to keep pushing something to keep it going? So for instance, here's a sled on snow. You push it and push the sled and it'll travel a distance and come to rest. On slick ice, it would travel further because the friction is smaller. On a frictionless surface, it would travel forever. It would never stop. Yeah? So for instance, in fact, if you went out in space and threw a fastball, a 90-mile-an-hour fastball, it would travel forever if there's no forces acting on it. Okay? In fact, there is such an example. These are two space voyagers that we sent out in 1977. They've gone out of our solar system, and there's almost zero force on them, and so they'll keep traveling at that speed for billions of years. Yeah. Until they encounter something. Yeah. So, in the absence of friction, a moving sled will stay in motion without anything or anyone pushing it. So, our intuition might suggest otherwise because we never encounter frictionless surfaces, or rarely encounter frictionless surfaces. Okay? So Galileo was the one who realized it, that if there was no friction, an object would maintain its velocity. Okay? And that's Newton's first law. An object has no net force acting on it, will remain at rest if it's at rest. If it's moving, it will continue to move in a straight line at constant speed. Okay? So,
That's the one that's raised, an object in motion stays in motion.
yep. So that's many ways of doing that. Okay? All right, Mr. Galileo was the one who discovered this, realized this. So why do we call it Newton's law?
He articulated it better.
No. So here's why we call it Newton's first law. Newton's second law was Newton gave us what if you apply a force on it, on an object. Okay? If you apply a force on the object, then it accelerates. Acceleration means change in velocity. Okay. So now let's look at this. What if the force is zero? What would be the value of the acceleration? If the force is zero, the acceleration would be zero. If the acceleration is zero, your velocity is not changing. So the first law really is a special case of second law, and so that's why we call it Newton's first law. Okay? Even though Mr. Galileo discovered it. Yeah. All right, so we'll give you an example of Newton's first law. Okay, let's say you're driving on I-4 at 70 miles an hour. You stick your hand out and drop an orange. What will happen to the orange? I'm sorry?
Down, roll up.
Fall straight down.
Okay, so fall straight down. Okay. So if you're going at 80 miles an hour, the instant you drop it, it'll be going at 80 miles an hour forward. So it'll drop on a curve. Okay. Well, everything in the car is going at 80 miles an hour. Okay. So now let's do the following. Okay. So here's a dummy in a car going at 80 miles an hour. Let's make a wall jump in front of the car. Okay, what will happen to the car? The car will stop. Will you stop? No, you keep going at 80 miles an hour till some force acts on you to stop you. Okay? So now I'll write down a couple of equations. You don't have to remember the equations, but we need it to understand what's going on. All right, what this equation is telling you is this is your final speed square, and this is your initial speed square. This is the acceleration. This is the distance over which that speed changed. Okay, so now you were going at 80 miles an hour, and let's say you need to be stopped. So that needs to be 0. That's 80 miles an hour squared. Okay? So this will have to be negative, but we won't worry about it. So this is the acceleration. This is the stopping distance. The smaller the stopping distance, the greater the acceleration has to be. You guys understand that?
Wait, can you, so it's the final speed equals the original speed plus.
This is the final speed square
Uh-huh.
is equal to the initial speed square plus 2 times the acceleration. So if you want to stop, this will be 0, and then, okay, so I'll bring this over there. Don't worry about the sign. It's a number. It's a This is a large number. So if you want the acceleration to be small, this has to be large. Large accelerations are bad for your health. They cause damage. Okay, so I'll give you an example. Let's say I climb up this building and I jump off. If the sidewalk stops me, that'll hurt. But if we do the same thing, I'll jump off the building except that we put a whole bunch of mattresses. I've jumped off the same height, but that didn't hurt as much. What happened?
Shorter distance, slower speed.
Shorter distance, greater acceleration. Greater accelerations is what causes damage. Okay? When you experience greater acceleration, when the acceleration you experience is greater, the forces on you are greater. And that's what causes damage. Okay? All right, so this person is moving forward. Okay. If this dummy gets stopped by the steering wheel has no give. It's stopping you in a very short distance. The accelerations are great, and that'll hurt. So how do you fix that problem?
Airbags.
Airbags. So airbags are stopping you over greater distances, so they're reducing the acceleration number. That's what airbags and seat belts do, all right? All right, so a force is a push or a pull. Here's an example of a pushing force. Anyway, every force has an agent. In this case, this is the agent, and that's the object on which it acts on. Okay. Okay. Now, here's the deal about forces. See, you can. There's the direction of the force. Now you can push harder, so the force would have a greater magnitude. Okay. A force has a magnitude, size, and direction. Okay. So forces are represented by vectors. Okay. So vector is a directed arrow segment. Okay. What is the difference between these two forces? This is a bigger force, that's all. Okay. The magnitude of this is bigger. Okay. And they're both pointing in the same direction. Okay. Now there are two kinds of forces. Okay. There are contact forces, and as the name suggests, to apply that, when an agent applies that force, it's in contact with the object. And then there are long-range forces. Okay. These forces act over a long range. You don't have to be in contact with each other. Okay. So the gravitational force is an example of that. Mr. Newton realized that every object attracts every other object in the universe. The force is an attractive force. Okay, so this object attracts this object, and that's the force exerted on this object. This object attracts this object, and that's the force exerted on this object. Now, Mr. Newton also realized the following. Let's say this object pulls him with a force of 100 pounds. What does this guy do? He pulls him with an exactly same magnitude force, 165 pounds. Okay? So you might have heard of action and reaction are equal and opposite. Okay, that's the third law of Newton. So here's an interesting fact about that. Okay, like I said, I weigh about 165 pounds. That means the Earth is attracting me with a force of 165 pounds. Okay, I'm not sitting still. I'm attracting Earth with a force of 165 pounds as well. Okay. So by the way, so this is Newton's third law, which is a Newton's law of gravity. It's a long-range force. It gives you the force. The force between the two objects is the gravitational constant times the product of the masses divided by the distance squared. R is the distance between the, to leave.
So this is Newton's third law?
No, this is Newton's law of gravity. Action and reaction are equal and opposite as Newton's third law. Okay.
So it's force equals what, I'm sorry?
G, the gravitational constant, times the product of the masses divided by R squared. Okay, so now here so this is the law of gravitation. It turns out that this number is very small. So for the force to be large, for the force to be significant, one of the masses has to be large. So for instance, every object attracts every other object. So there's a force of attraction between two people, for instance. Okay. But the force of attraction between two people is roughly the weight of your hair. That's why I'm not falling toward that. But if I jump off the table, I'll fall toward the earth. The earth is massive. Okay, so that force is significant.
What does the R represent?
The distance between their center of masses, between the centers of the two objects.
Okay, so R is distance, okay.
Yep. All right, so we'll be talking about two kinds of forces, contact forces and long-range forces. So for contact forces, of course, the object have to be in contact. Forces are represented by vectors. Vectors are directed line segments, okay? So the direction of the vector tells you the direction in which the force acts, and the length of the vector tells you how strong the force is. Okay. So for instance, this person is pulling this box. Okay. Now, and when we analyze situation, we don't want to draw all of that. So what we'll do is we'll do a simple diagram like this. This object is represented by this point, and the force is given by that. And this is a free body diagram. All right. Here, in this case, the box is pushed against the spring. And what does the spring do? It will push back. Okay, so the box is represented there, and there is the spring force. Here's the box. Let's say while it's falling, what is happening? The earth is pulling it down. Again, the force of gravity. So here's the box, and there's the force of gravity. Okay. So these diagrams are called free body diagrams. Okay. All right, what if there are multiple forces acting on an object? Okay. So let's say here's this object, and there are these two forces acting on this object. Okay.
Move toward the greater force?
So, well, I'm glad you mentioned that. So, before we do that, let me show you how to add forces. Okay, so here's how you add forces. Here's how you add vectors. Okay, so if you have two vectors, A and B, here you denote vectors generally by capital letters with an arrow on top. Okay, so if you want to add these two vectors, here's how you add them. Okay, you take the tail of the second vector, bring it to the head of the first vector, and the sum of the two vectors is that. So there is B, and this is A plus B. Okay, so now let's go back to our diagram. So that's how you add vectors. And in fact, you can do this to as many vectors as you want. So here is adding 5 different vectors. A, B, C, D, E. Okay, you keep moving the tail of one vector to the head of the next vector and so on. And the sum is from the tail of the first vector to the head of the last vector. Okay, so that's how you add vectors. All right, so now let's ask what happens when you have multiple forces acting on an object. Okay, so the reason we learned that was following to, so if you have multiple forces acting on an object, what you can do is add those two vectors, and here is the sum of those two vectors. See, you can bring the tail of that over there, and there is the sum of those two vectors. Okay. Now here's the deal. So there's the object. We are going to represent it by, these are the two forces, F1 and F2. Our object is represented by this point, and here's what we realized over time. Okay, if on this object you have these two forces acting on this object, okay, on this object you have these two forces acting, or just this one force, which was the net force. You can't tell the difference by looking at the motion of the object. The motion of the object would be identical. Okay. So the effect of the net force is the same as the effect of all the forces acting together. Okay. What is your weight?
Force gravity has any body.
And very good. So here is the Earth. The Earth pulls you down, and I said my weight is 165 pounds, but that's the magnitude of the force. Which way is the force directed? I'm sorry? It's directed towards the center of the Earth. So you are being pulled toward the center of the Earth.
But the Earth is
Um,
pushing at you at the same rate, so it would be in both directions.
Oh, well, the ground pushing you on the Earth, that's why you don't go into the Earth. Okay, so for instance, if you try and stand on the ocean won't be able to push you. You'll fall down. Yeah. All right, but the force of gravity on you is toward the center of the Earth. So that's why the Australians don't fall off the Earth. Okay, they are being also pulled toward the center of the Earth. Okay. So this is the force, and the magnitude of the force, the strength of the force is what's your weight. Okay. So when you say you weigh 165 pounds, what you're saying is the magnitude of the weight of the force. Okay. The gravitational pull of the Earth on the object near the surface is called its weight. Okay. So, by the way, so the stuff in my body is the mass. That gives you the mass. My mass is the same no matter where I am. That should be Mars, by the way. So my mass is the same whether I'm on Earth, Mars, or the Moon. But my weight, the force with which this object pulls me, is different. My weight on Earth is, these are different units, 500 newtons. Here it's about 185 newtons. So I weigh 2.5 times less. I would weigh 2.5 times less on Mars, and I would weigh about 1/6 on the Moon. Yeah. So an object's weight force vector always points toward the center of the Earth, no matter where on the surface you are. So whether here or there, you're being pulled toward the center of the Earth. We'll talk about spring forces. Spring forces, you encounter these everywhere. So here's an object attached to a spring. So if you push the spring, if you compress the spring will push back on the object. So if you compress the spring pushes back. And if you pull the box, if you stretch the spring will pull back. All right, so here is the uncompressed. So position of the spring, and there's the position of the object. If I compress the spring, it pushes back. What is the spring trying to do? It's trying to bring you back to your original spot. If you stretch the spring, it's pulling you back. It's trying to bring you back to your original spot. So the spring force is a restoring force. Okay? So it is like this. So if you think of a marble in a valley, you disturb it, gravity will pull you back. Okay? So here in this situation, it's a restorative force, restoring force. We'll put the same marble on top of a hill, and now gravity is not restoring it. Okay? In this situation, it's restoring. Okay? So the spring is a restoring force. And here's another thing about the spring. Okay, so let's say you pull it this far, and we'll call this distance x. The spring force is minus k times x. Again, you don't have to remember all these formulas. But the further you stretch, the greater the force. What is the negative sign telling you? If this is positive, the spring force is in that direction. Okay. If the object is here, this is negative x. Negative times negative x will be positive. The force will be in that direction. This fellow is called the spring constant. Spring constant. The stronger the spring, the stiffer the spring, bigger this number is. Okay. I'm sorry? The stiffer the spring, bigger that number. Yeah. So for instance, your car has springs that are 25,000 newtons per meter. What that would mean is you have cars, springs in your car. You'd have to compress the spring that much, 250 people would have to stand up. Okay. All right, we'll talk about tension forces. Here's a rope pulling on a sled. Okay, so the rope is, when you pull on the on the sled, it stretches a little like a rubber band. Okay, so the rope is under tension, and this tension force is pulling on the sled. Well, the force is applied in this direction, and the sled will move in that direction. Okay, because there are other forces involved. Okay. Now here's the deal with the tension force. A tension force can only pull. You can't push an object with a rope. Okay, so tension can only pull. Okay, so tension forces can only pull in the direction of the string. Yeah. So now let's look at how the tension arises. Okay, so here's the rope attached to this object, and you're pulling on this rope. Okay, so here's the model. Okay, the rope is made of many atoms, and the forces between atoms can be modeled by springs. So you can think of springs attached. The atoms are attached by springs. Okay, so now here's the rope. Okay, so here are the atoms. So when you pull on the rope, what you're doing is you're pulling on this layer of atoms. This layer of atoms stretches these springs, and then that pulls this layer of atoms, which is pulling the next layer of atoms, and so on, and then you're pulling the box. Let's say you apply the force of 100 pounds. What that means is this force plus this force plus this force plus this force, all those added up to 100 pounds. Right? You guys understand that? And then that layer pulled with this layer with the force of 100 pounds. Eventually that got transferred to them. What happens when you decide to pull harder? Let's say you pull with the force of 150 pounds.
Get more stretch.
Very good. These guys stretched more, And that's what that equation was telling you. Okay? When there was a greater stretch, the force was greater. Okay? What happens when you let go?
It'll snap back.
Yeah, all the springs go back to their original length, okay? And the forces go to 0. All right, so you'll see this everywhere, okay? When you pull harder on the rope, the microscopic springs stretch a bit more, okay? Increasing the spring force. Okay, so now this is what's happening when, let's say you put a book on a table. Okay, the atoms of the table are modeled like that. And when you put the book on the table, they compress some of the springs, and these springs are pushing back on the book. And all those pushbacks added up to this total force, which is, since the book is not going through the table, that is equal to the weight of the book. Okay? So all these pushbacks, these are, the total force is perpendicular to the surface. Okay, it's not parallel to the surface, or not at an angle, it's perpendicular to the surface. Okay? And that's why it's called a normal force. Okay? Normal in mathematics means perpendicular. Okay? So it's a perpendicular force. Okay? So by the way, if you sit on a bed, the spring in the mattress compress and exert an upward force on you. Stiffer springs, what does stiffer springs mean?
Let's give.
K is greater. For the same force, if K is greater, then you have to compress or stretch less. Okay? Less give. Okay? So that was the equation. So, okay, this is the amount of stretch or compression. That's the spring constant. Greater the spring constant, greater the force exerted. Okay. Stiffer springs would show less compression, but still would exert an upward force. The compression of extremely stiff springs might be measurable only by sensitive instruments. Okay. So why do we talk like this? Your bones are also springy. Your tendons are more springy than your bones. Okay. But everything in your body is springy. Okay. And in an elastic, when I stretch an elastic, okay, and so you take a rubber band, stretch it, and let go, what happens to the rubber band?
It snaps back to its normal
And
shape.
it'll step back, but if you let it fly, it'll fly. So what happens? The elastic energy stored can be converted to motion. That's how kangaroos jump. We'll talk about this in the next chapter. Their tendons will stretch. They store energy in the stretched tendon, and 90% of that is given back in the next chapter. Okay. All right. So the figure shows a book resting on the top of a table. The table may not visibly flex or sag, but the book compresses the molecular springs. Okay, so it does compress the molecular springs in the table. The compression is very small. Okay, so right now the molecules on the table are compressed. Okay. What happened to that compression?
It's more
Stronger.
Yeah, increase. So that we say that the table exerts an upward force, and that's called a normal force, again because it's perpendicular to the surface. So an object resting on the ground compresses the molecular springs holding the ground together and pushes the object up. So when you're standing, those molecules are compressed, and that's what's pushing you. Okay? That doesn't happen when you're trying to walk on water. Same thing happens when you push on a wall. The atoms there compress and they push back. Okay, now we'll talk about friction forces. Right, so you saw that when this thing slid, friction forces stopped it. Okay. What direction was the friction force?
The opposite of the.
Motion. Okay, so now it was in this direction. If the object is moving in this direction, it's the friction forces switches with that. Okay. So friction forces are always in the direction opposite to the motion. Why does friction force arise? What causes friction? What do you think causes friction?
Connectivity.
Yeah, so the molecules of the table attracting the molecules of the solid. Is there a way to increase that friction?
Increase, what do you call that? Like a file. The molecule.
So it's attractive force. So put glue on here, and attraction will increase. Friction will increase.
If it were, so if the surface was, this is just a strange thought, sorry
Yeah.
guys. But if it were,
Smoother.
no, file, like
Yeah,
on a
rougher
file,
surface.
Yes.
Yeah, yeah.
that would create more surface space and therefore.
If you're increasing the contact area, then if you're having more molecules attract each other, then it'll increase friction. Okay. So friction forces are always parallel to the surface. Okay, so I'll illustrate this. Okay, we'll talk about. Okay. So there was friction force between this. Now I press down on it. Is the friction increasing?
Mhm.
Why did the friction increase? So when I press down, I'm moving the atoms closer together, more atoms were attracted to each other. Okay? So friction force depends, so now when you press down on it, the normal force increases, so friction force will depend on the normal force. All right, so friction force is always in the opposite direction. Now there are two kinds of friction, okay? So when this object is moving, this is called a kinetic friction force. Friction forces are denoted by small f, they're a force. And it's kinetic friction force when the object is moving. And there's another force called a static friction force. All right, let's see where does this arise. Okay, so let's say here's a box sitting on the floor, and I pull with a force of 50 pounds. If the box didn't move, why did it not move? Because there was a friction force in the opposite direction, 50 pounds. Now let's say I pull with a force of 100 pounds. It still didn't move. Well, this static friction force increased. Okay. So it seems like the bonds were strong enough. Their strength could vary. If they needed to increase, they could apply that force. Okay. So the static friction force, so if I'm not pulling on it, what is the static friction force? 0. Okay. So the static friction force can be anywhere from 0 to a maximum value. Because there is a force I can apply and get the box moving, and that will equal the maximum static friction force. Okay, so, and what is the direction of the static friction force? If the box is trying to move in this direction, the static friction force is in that direction. Okay, why would we talk about this? Yeah. Is this important in our life? Do you know anywhere where static friction force is important? Okay, so here's an example. Okay. When you try, go ahead.
When driving.
When driving.
Braking specifically.
No, even driving. So when you're trying to walk, here's how you try to walk. So what am I doing? I'm trying to push back. I'm pushing back. Okay, if my legs slipped, I'm not walking. I'm pushing back, and the static friction force is acting forward. That's what's propelling me. So if you didn't have friction, you couldn't walk. So again, let's make sure. So when you're pushing back, the force of the push, it's the static friction force that's propelling you forward. Okay. Similarly, so what does your car engine do? What does your car engine do?
It creates the force.
It just spins your tires. Okay, so for instance, let's say you can take your car to get your oil change when they have it up on the ramp. Turn on the engine, all that'll happen is your tires will spin. Okay. So your car tire is spinning. Okay. This point is not in contact. What is happening is this point of contact. So if you were on ice, that'll just spin. This point is trying to go in that direction, but the static friction force prevents it from spinning. So the point of contact is at rest, and that is what is propelling your car. Okay, so when you accelerate, it's the static friction force that accelerates your car. You guys have seen drag racing, the quarter-mile drag race? Okay. So in a quarter mile, you're trying to get to the end as fast as possible. And before they do their run, what do?
They melt their tires by spinning them.
They heat their tires by spinning, because the maximum static friction force, again, I'm just writing an equation. The maximum static friction force is equal to mu s. It's a coefficient that measures the stickiness of the two surfaces times the normal force, and the normal force in this case is equal to the weight. So when they're burning the tires, they're making this number bigger. So the maximum static friction force is greater, and you can accelerate faster. Okay. All right, so we use friction forces in our life all the time. Okay, they're important. So we have two kinds of friction forces: kinetic friction force and static friction forces. Okay. All right, friction forces are when two solid surfaces interact. When you move in a fluid, there's a friction force, but that force is called a drag force. It's just got a special name to it. Okay, so friction forces exerted by fluids are called drag forces. Okay, and we're talking about this because fish experience drag forces. Okay, birds experience drag forces, and so on. Okay. All right, resistive forces are also experienced by objects moving through fluids, gases, and liquids. Okay. The drag forces points in the opposite direction of the motion. So when this is falling down, the drag force is in this direction, and if I toss an object up, so even the drag force is negligible. When the keychain is going up, the drag force was in the downward direction. When it's falling down, the drag force was in the upward direction. Okay. Drag forces can be large for objects moving at high speeds or in a dense fluid. Okay. So so here's a problem. For a small particle moving in water, such as swimming paramecium, drag is the dominant force. Okay, so for these single-celled animals in moving in water, drag force controls their life. If they want to move, they have to push. Soon as there's no coasting in for these guys. Soon as they stop pushing, they stop. Okay. So drag forces are dominant in them. Okay. Thrust forces, so for a rocket, yeah, so generally for rockets, okay. So when a rocket is sitting on the launch pad, there's the weight, okay, and that's preventing it from taking off. So you have to apply a thrust force Okay, generally, the rockets on launch pad, the thrust force is about 1.7 times the weight of the rocket, roughly. I mean, generally that's, so at 1.7 point. So the thrust force is greater than the weight and it'll lift off. And what is the deal with rockets? This thrust force generally is constant, and as it's burning fuel, its weight is decreasing, its mass is decreasing, and force is mass divided by times acceleration. So as the mass decreases and the force is the same, it accelerates faster and faster. Yeah. Now, how do you generate thrust? How does the rocket generate thrust? It has to spew out exhaust gases at high speeds. So the thrust force is it's a recoil force. It's a chance, essentially, if you shot a gun, when you shoot a gun, you recoil, and that's what's happening in the okay. So the more mass you exhaust and the faster you exhaust, the greater the thrust force. Yeah. Now the animal world uses this. So these guys have no fins, or scallops have no fins or anything. And if they have to run away, what do? Or if they have to go to a new location to find food.
Is there propulsion, water propulsion?
They turn on their rocket engines. The water, they shoot out jets of water and they propel in the opposite direction. Okay. Squids do that. Okay, so squids have rockets as well. Yeah. So a scallop forcibly ejects water from the rear of its shell, resulting in a thrust force that moves it in the opposite direction. Yeah. So what can forces do when you apply force? Okay, we've been writing this equation. When you apply a force, you have an acceleration. Accelerations change velocities, and so you can run away from predators. Okay, or you can use that to catch prey. Yeah. So Newton's second law says that again, you want a greater acceleration, you have to apply greater forces. If a tiger is chasing you, you want to apply all the force you can. We already saw this. If several forces are acting on you, which way do you move? How do you figure that out? All you do is add up all the forces, find the net force, and the net force is the direction in which you move. So the sum of these two forces is a force in this direction, and the sum of these two forces is a force like that. And so your acceleration will be this one. Okay. And by the way, so the units of mass are kilogram, the units of SI units for acceleration are meters per second square. So the units are kilograms, meters per second square. And in physics, we name combination of units after people who've done work in there. And this is called a Newton, after Mr. Newton. Okay, so the units of force are newtons in
Under the M, what is that?
meters per second square. So units of acceleration are meters per second square. Okay, here you saw that that's how you add vectors. There is the sum of two vectors. You can add several vectors together. Yeah. Now, this is some mathematics that you don't have to remember, but anyway, in case you need it. So here's this vector. You can write every vector as a component in terms of its component. Here's the x component of the vector. Here's the y component of the vector. So your vector is the x component plus the y component. Your vector A is, here's the x component. This is the unit vector in the x direction, unit vector in the y direction, and so on. Here's the components given in terms of the magnitude and direction. And again, I'm just putting it out there. You don't have to worry about that. All right, now let's apply these forces to our lives. Yeah. So your muscles apply apply forces in your body. Okay? Muscles is what provide forces. And I don't know if you guys know this, muscles can only contract. Okay? So if you want a body part to move in two directions, you have two different muscles doing it. Okay? And muscles are, so here's a muscle that's attached to this bone and this bone. Okay, when this muscle contracts, it moves this bone in that direction, the leg in that direction. Moving two bones closer together, and this muscle is called a flexor muscle. Okay. Now, if you want to move the leg in this direction, now you want to stretch your leg, this muscle is not doing the job. It's this muscle that's doing the job. Because when this muscle contracts, it pulls this muscle like that way. Okay? So when a muscle is separating two bones, it's called an extensor muscle. When it's bringing two bones closer together, it's called a flexor muscle. Yeah. So to move this leg in two different directions, you had to employ two different muscles. And why was the reason? Why did you have to do that? Muscles can only contract. If they could contract and stretch, then you would have had to have only half as many muscles. All right. In your arms, okay, so this is the flexor muscle, okay, so that is attached to the shoulders. Okay. And of course, that the joints provide frictionless surfaces for bones to rotate about. And of course, if that frictionless surface becomes, low friction surface becomes high friction surface, what happened? And that's arthritis. That's arthritis. Okay? And here it hurts like crazy. Okay. All right, so this is flexor, and this is the extensor muscle. All right, now we'll answer the question. Why do you have so many muscles?
All of our parts have to move.
What's that?
Because all of our parts have to move. And in different directions.
Okay, so now you're barking at the right. So here's why you have so many different muscles. Okay, what can a muscle do? It can only contract. And when it contracts, think of it as a spring. When it contracts, what is it doing? It's pulling whatever it's attached to. Okay, so it's applying a force on whatever it's attached to. Okay, so let's look at this diagram. When this muscle contracts, it's applying that force. When this muscle contracts, it's applying this force. When this muscle contracts, it's applying this force. Okay, if only those three muscles contracted, then you could apply a force like that. If all those muscles contracted, you could apply a force like this. If you recruited more muscles, then you could apply a force like that. So you have all these muscles so that you can apply a force in many directions with different magnitudes. Okay? So again, there are hundreds of muscles in the human body allowing forces to be exerted in almost any directions. Okay? So if you had just 2 or 3 muscles, you could only apply forces in very few directions. Okay? So for versatility is why you have so many different muscles. Okay? So I find this funny, so I got to tell you this. Okay? You guys have heard of topology? Has anybody heard of topology? Yeah?
The study of geographic heights and valleys, peaks and highs.
Okay, yeah,
Is
okay.
Is that topology or no?
That's topography, yeah. So,
Topography,
yeah.
sorry.
So this is topology is a branch of mathematics. What's that?
That's what I thought of too.
Yeah. So they study shape. This. All right. So in topology, A cup is the same as a donut. How do you ask? Okay, so you think of this as you make, everything is made of putty, and as long as you're not tearing, if you can reshape the object into a donut, they're equivalent objects. Okay, so that's topology. Okay. So everybody agrees that a cup has one hole in it, and a donut has one hole in it,
Yes.
right? Well, where? Let's see a cup. Who's got a cup? Nobody's got a cup. Yeah.
I'm sorry.
Oh,
So the cup and the donut are the same.
not the same.
Okay, but what if the cup is so much more mass, if it's twice the
Yeah,
size of the
yeah.
donut? Or we're not
Oh,
talking relation
yeah.
in size,
Yeah.
right?
I mean,
All-
technically a cup has 2 holes, but that's fine.
With that?
Technically a cup has 2 holes.
No, it doesn't have 2 holes. The bottom.
The hole
it's
goes
not
all the
good.
way through.
The hole doesn't go all the way through. It's got only one hole. Okay, so you guys understand? Okay. Cup.
I swear, some of you science guys are just making crap up to make crap
Hey
up.
man.
Like,
Well, if you take a cup and flatten
just
it,
to be
and
pedantic,
spread
and
the
it's
mass around the
ridiculous.
handle, that's a donut.
Yeah, exactly. See, he buys it. We're on the same team. So here's my claim.
So if you dig in the ground, what's
Go
that
ahead,
called?
go ahead. Go ahead.
If you dig in the ground, what's that
Yeah,
called?
you have a big donut if you.
Yeah, but
No, there's a
what is it
bottom.
called? What is it called now when we dig in the ground?
No, you
We
go all the
call
way
a
through.
hole.
Is there a bottom to that hole?
Oh, yeah, if you dig all the way through
Yep,
the
so the
earth.
cup has 2
And
holes.
people have many holes, but they don't go all the way through.
No, so you are equivalent to a donut.
I mean, technically, if you dig a hole, that's a well.
No, hey.
I mean, I've met a lot of people I would definitely call a donut, but I,
Especially in
So,
Florida.
so, people have one hole going through their donut.
You don't want to.
All right, hey, now we're coming to an important point. You guys need to get serious. You gotta take an exam now. All right, so we have these things, and so you need to be able to close holes. You have sphincter muscles. These are circular muscles, and what can muscles do? They can only contract. So when sphincter muscles contract, they close. Okay. So you learn this. So in a pipe, when you want to make a fluid flow, if you want to make a fluid flow in this direction, you have to have higher pressure here and lower pressure here. Okay. In your stomach, you have acid. Okay. The pressure in your stomach is higher than in your esophagus. The pressure in your esophagus is lower. What should happen to all this acid? Yep. You lay down and it should be coming up, flowing into your esophagus.
I have GERD, so it does.
It does, see? So what's the problem? What's the problem with this donut?
My sphincter muscles are
Our
not strong enough
sphincter
to
not-
hold
yeah.
the acid down. It's either not contracting enough,
Right.
or it releases and
So,
contracts and releases and contracts.
There's a
too
defective
often.
donut.
I'm a defective donut, thank you.
Yeah. You guys understand? So the sphincter muscle has to do that, okay?
You were feeling okay and then you showed up to class. and-
Yeah.
No,
Well, that's my job, that's my job. Yeah.
To be honest, I got pulled over for speeding before I came to class, hence why I was late, so I was not feeling good at all today.
Well, they say, when you're down, kick them,
It just adds to it, so yeah.
Yeah, that's the world kicks you when you're down. Okay, so here's another place where you have a sphincter muscle. Okay, so this glass has a focal length. If I want to change the focal length, I gotta order it, and 2 weeks later, I might get one. But your eye is an amazing instrument. I look at that, my focal length has to be different, and then I'll look at this. In a millisecond, my focal length changed. How did that happen? Okay. I'm sorry?
Contraction of your pupils.
Yeah, not your pupils. So your lenses eye lenses are suspended by a ciliary sphincter muscle. Okay, so there are these cords suspending the lens. Okay, when it contracts, it's become smaller, this opening has become smaller, and the lens becomes thicker. When the lens becomes thicker, then you can focus closer objects. When I want to look at that, my muscles relax, the lens became thinner, and my eyes are focused.
So when they do LASIK, does that, do they change something with the muscle and how it contracts?
No, that's the lens.
No, it's just the lens.
That is,
Yeah, so when the lens becomes thicker, so on the fly, you're able to change the focal length of your, like a magnification, focal length of your lens. Yeah,
Why
so,
haven't we been able to reproduce the lens itself?
I'm sorry?
Why haven't we been able to reproduce the lens itself?
What do you mean?
I mean, I figured that would,
Humans have not made it to that point yet.
yeah.
No.
I'm sure somebody's trying.
You mean
Why
an
can't we
artificial
recreate
lens?
the lens? Why have we not been able to recreate the lens yet?
Because we can make like a hard lens that obviously can't be contracted, hence glasses.
No, you can't make any man-made thing it's changing your focal length on the fly. I mean,
It has to connect with your brain.
no, yeah. You all forget, you have the most powerful computer dam attached to your shoulders. That's doing all the calculation. You look at that site and it's controlling how much it should thicken and thin. And you can't have that much computing power for cheap enough.
Technically, that's just electricity, increasing or decreasing electricity, which is.
Yeah, okay, maybe I don't understand your questions. Go ahead, repeat your question.
It's okay.
All right, so again,